Good morning, physics. This is Mr. Hausman. We're going to be taking a look at the electric force today. The electric force is kind of our final topic in the area of static electricity. And what we mean by the electric force is the push or pull that we feel between charged objects. It could be the force that lifts your hair up when you're touching the Van de Graaff generator. It could be the static cling in bed sheets, maybe in the wintertime when we get a lot of static electricity, or maybe clothing that you wear. If you ever wear like Under Armour or synthetic clothing, sometimes you'll notice that it kind of can be clingy to your skin. So we're going to try to find out, how does the amount of charge, goal number one, is to talk about the amount of charge, and the symbol for the amount of charge is Q. It just is. It's one of those weird things. And the unit for charge is in coulombs. I do want to warn you that the amount of charge we're going to be talking about are very small. We're going to be using scientific notation. However, we're going to remember that if you look at the number in the front of the scientific notation, you can do easy comparisons. No big deal. Goal number two is going to be to investigate how does the distance between two charged particles, how does that affect the force? So let's begin with a quick summary of what is this force again? Well, it's called the electrostatic or the electric force, and it is the push or pull between charges. It can be, let's start with two charges at a time. So what if we have two opposites, right? Positive and negative are opposite charges of each other. Well, according to common sense and some of our background information, two opposite charges tend to attract. That means they pull each other in. And that's kind of sometimes how they say it about humans, people, their personalities. If you're opposite of someone, sometimes that makes it more interesting, and so you're attracted. Two charges that are the same, two positives or two negatives, they tend to repel. And repel is just a fancy word for push apart. So let's remember that. Like charges repel and opposites attract. But today's question isn't really to describe do they push or pull, it's how hard or how much force do they exert. And that's governed by a principle that's been discovered in the 1700s, and it's called Coulomb's law. Okay, so let's take a look at an investigation you're going to do. So this is in assignment number 7, but the text is really small, and it's kind of wordy. So you're going to determine the law of the electrostatic force, and you're going to discover it by making some observations. So here's the website. I've already got it loaded on the next slide, and we're going to look at that together. So don't worry about having to find that site. But if you wanted to, that's where you can find it. So in this virtual world, which is how we're teaching a lot of things these days, there are two charges. We call them Q1 and Q2. They are separated by a distance, and that's measured with a ruler. And all of these things are movable. You can move them around and see how they interact. You can also change how big is the Q. So this slider can go down to as low as 5 units of charge and go up as high as 50. And Q2 can also go up and down. So here's where we change the amount of charge. So here's the little investigation we're going to do. I've already set it up, and I've had a little trouble with this, so we're going to make sure it works this time, is we're going to start off with a baseline. 5 units of charge on the first Q, 200 on the second one. And we're going to measure how much force. And it should come out to be 1 Newton when they are 3 meters apart. So our experiment isn't just to confirm that, it's to then make a change. Which one of these numbers would we like to change first? Let's change Q1 first. Let's change it in a way that makes kind of sense, because our brain can kind of understand like doubling something. So if you have a $5 bill and you double it, you've got 10. If you double a 10, you got a 20. Most of us can do that kind of thinking in our head. So we're going to double Q1, but we are not going to double Q2. That's the experiment. And we're going to ask how much force is there. Then we're going to double Q2, but put Q1 back to 5. And we're going to write down how much force we got. Then we're going to double both of them. What if we have the 5 doubled to 10 and the 200 doubled to 400, And what is that going to do here? So we're going to do 3 experiments, and then we're going to come back and write in the data. And we're going to see how does changing the amount of charge affect the force. So let's go ahead and do this. I have these numbers sort of remembered, so it should be pretty quick, okay? So we reload the page. This is where things get a little bit ornery. I've had to redo this a couple times. And so I've moved them to 3 apart. I've moved the sliders down to their lowest levels. And as I said, the experiment starts at 5 and 200. And notice the force came out to be 1 Newton. So that's kind of like when they're this far apart, they attract each other with a pretty small force. But what happens the moment we double the top one? Let's move that up to 10. You might say that was a very small change. You know, you only went from 5 to 10, but it was really twice as big. And so the force, I can't circle it, but look at the force on the top of the page. We got about 2. Now, let's move that one back to 5 and move this one to 400. It looks like it's a bigger move, but really it's still just doubling. There we go. And notice anytime you double either one of the charges, you get double the force. So apparently, the charges go the same direction. So if you double it, it's going to increase by double the force. Now, the third experiment was to not just double Q2 and leave Q1 down at 5. It was to move both of them up to double. So let's move this up to 10. That's double 5. And 400, we're still on the doubling of Q2. And look what happens on this page. So instead of, if you double both of those charges, the quantity is 4 times bigger. Let's write this down in a summary table and see if it makes sense. It may be a little tough. So let's put in some answers in green. So we doubled one variable, the first slider, the first charge. It only moved a little bit, but that's actually twice as big. And we got twice the force. It went to 2 newtons. Then I moved the first charge back to 5 and the second one to 400, which is double, and we got also 2 newtons. So apparently it doesn't matter which one you double. If you double one of your charges, you get twice the force. Finally, we doubled both of them. We doubled 5 and we moved it to 10. We doubled 200 and moved it to 400, or kept it at 400. And did you notice? The force went up 4 times. So that's a pretty interesting relationship. If you double one of the variables, it doubles the answer. If you double both of them, it goes up by 4. So Mr. Coulomb figured out that the formula for force is directly proportional to Q1 times Q2. And he noticed that because if you double this Q, it doubles the force. But if you also double the other variable, you then get 4 times the force. Do you see how it works? 2 times 2 is 4 times bigger. It's like doubling something twice. So we say that is a direct proportion. That's what it's called when one variable pushes another variable in the same direction. Doubling each of those caused it to quadruple 4 times, and that's a direct proportion. Okay. Now let's take a look at how distance affects the amount of force. So we're going to start with 5 and 200. We already know those charges. And we're going to move them up 1, 2, 4, and 8. Do you notice that pattern is continuously doubling? Double 1 is 2. Double 2 is 4. Double 4 is 8. So maybe you might predict that it's going to cause the force to get bigger, just like it did with Q. And we'll see if that's true. So let's reload the website. And let's move these down so that they are 1 meter apart. Okay. Whoop, there they are. Now, you can't even see the force arrows. They're so large. Let's move these down to reasonable levels. Hey, let's reload that page. Sometimes it gets a little picky how I combine things. 1 unit apart, 5, 200. Great. Okay, so I think at a distance of 1 meter from center to center, and the Q's are at 5 and 200, we're going to remember that that number is 18, or really it's closer to 19. I'm writing that down because I might forget. Now let's double the distance, right? If the distance between them is 1 centimeter, now let's make it 4 centimeters, or 2 centimeters. Whoa, did you see their force arrows? They went from 19 down to like 3. And then if we double them again and go out to 4, 1, 2, 3, 4 boxes apart, it's now down to 0.7. Wow, it's like do you guys get what's happening? It's like falling off. And then double 4, 5, 6, 7, 8, and now it's at 0.2. It's kind of like the force gets much weaker with distance. So let's write down what we saw. 1 meter was about 1 meter apart was about 19 newtons. 2 meters was 3 newtons. Well, that's not a doubling, guys, right? In fact, that's about a quarter. And then you decrease it again. You double the distance, and it goes down to 0.7, and 8 meters down to 0.2. And I'm noticing that as my distance increases, my force is decreasing a lot. And that is called an exponential decrease. And it's a little hard to figure out where that comes from, but essentially, when you double this, it's approximately 1/4. Doubling each one is reducing it by a quarter of what it was before. So Coulomb's law, he didn't just leave the Q's up there in the formula, Q1 and Q2. He realized that the distance factor was more important, and he said that, and he knew that because it is a squared factor. It's an exponential factor. So Coulomb's law is kind of a sophisticated formula that allows you to predict. And we now have seen that the Q's, think about the experiment we did before, they were directly proportional. But the distance is said to be inversely proportional. In fact, it's called an inverse square. That's d to the second power. Now, for fun, in case someone does more science in their future, there is something called a K constant. And we don't need to know exactly what that is, but if you were to plug in all of these values, real measurements, and that is pretty tough work, you would get the absolutely correct force. And the K value for the electric force is actually a huge number. It's 9 times 10 to the 9th. That's 9 billion. And what that kind of tells you is that this electric force is a very strong force. It's the force that keeps matter together. Okay. There's a little more to this lab, but this part's kind of the fun part. All you have to do is observe what happens to the aluminum can. Now, all of this is applications of the force. So I have a different simulation. It's from the same website. And this is an aluminum can, and you're looking at its end, right? This is the end view. And we have different things that we can push and put near it. So what if we bring a rubber rod, maybe it's a piece of plastic or rubber, and you notice that no matter where we put it, the can tends to roll toward it, pretty slowly at first. If we bring it close to the can, do you notice the can kind of accelerates more? It must be because of the inverse square law. The closer two things are, the stronger the force. The farther, the weaker the force. Now, if you give it enough time, it will always attract. So let's figure out why that's happening. Why would a piece of metal be attracted to a charged rod? The metal's not at all charged, right? Well, it has to do with the fact that in a metal, the charges can move. And we would say that this can is polarized. No matter where we put the negative plastic wand, the electrons move away, and it leaves the front face of the can. The can that's facing the wand is always going to be the opposite charge is the wand, so it's positive. And we know that opposites attract. Okay, so let me put the plastic wand away, or the rubber rod away, and let me put in the glass wand. So glass, when you rub it with something called silk, you guys know what a silk fabric is, it can become positively charged. And it seems to attract. In fact, it seems to attract better. In real life, it's really hard to charge a glass wand. I've tried it, and it doesn't work so well. So do you notice that when it's far away, it's weaker? When you put it close by, it attracts very strongly. And look what's happening. It's the exact opposite. Since the wand is positive, in this case glass, the electrons, besides jittering all over the place, are trying to get close to it because they're attracted by the electric force. And we would say that inside the can, the charges are polarizing, and it causes an attraction, right? Opposites are attracted. Now you can put in both of these guys, the glass rod and the rubber rod, at the same time. You used to be able to. Maybe you can't. Oh, the rubber rod is not appearing. Oh, maybe it's way up there off the screen. Yeah, I think it is, but it needs to be reset. So I'm not quite sure why, but I must have pushed it out of the way too far or something like that. I think I see it right up above the word aluminum. So going back to this page, which is part of the activity, is to describe what you saw. Well, when you bring the glass wand down nearby and it's positively charged, we know that the can moves this way. And so let's draw kind of what we see. We see a positive wand, and in this case, the electrons moved close to this side. The positives stayed in the can, stayed evenly distributed. The positives never moved. So we saw an attraction. And then you do the same with the rubber rod. But the rubber rod is negative. That was maybe rubbed with fur. But inside the can, now the electrons are going to run to the other side, and the protons are going to be evenly distributed. But look still what happens. The near side and the wand are still attracted. So both of those. It also proves that a neutral object, like a piece of metal, it can also be attracted to a charged object. Okay? We don't really need to do an experiment. If you wanted to do both, you could. But that's one of the analysis questions. And then the very last step is something about electric fields. And it's going to be really short and quick. And we're going to go and observe what do we get when we have a single positive in the middle. And an electric field shows the direction of forces around that positive object. It could be a proton. What if it's more positives in the same exact area? What if you pile up a whole bunch of positives, but they're still close together? And then we're going to do something also where we put a negative in the field, and we're going to draw their shape. And we'll come back to this page. So let's do a little refresh. Okay. So here's how it works. You put in a positive, and you drop it anywhere you want. And believe it or not, just immediately, the software starts drawing the shape of the electric field. And what this is showing is what would happen if you dropped a positive charge nearby, near this positive charge. And the answer is it would get repelled away. But why are the arrows so faint, not very dark out here, and why are they dark here? This shows that it's stronger. This shows that it's weaker. And that's the difference with electric fields and distance. The farther away you are, the weaker the force. So it's very similar to Coulomb's law. Okay? So can you remember that? And let's draw that. Let's clear the screen. Here we go. Oh, we're having one of those. Yep, there it goes. Okay, we can clear the screen. Let's go back here and draw what we saw. What we saw was arrows going away. They were very small, but the arrows always point away from a positive object because that's the direction a small little test charge would go. If someone said, hey, let's test it, let's drop in a proton. We're going to go back and do 2 more experiments, and then we'll finish up with this data page. Okay. So I think we can even get rid of these guys. There we go. Let's reload the website, finally. Okay, now what if we add a bunch of positives and put them all on top of each other, near each other? Can anyone see what's happening to the picture? I'm starting to notice that these arrows out here in the corners, they're not as faint anymore. They're getting a little darker. And the arrows closer to the charge are getting even darker. Well, they may not be getting too much darker, but I'm noticing that the intensity or the strength of the field. So what we're proving is that the bigger the charge, I think I've put 5 or 6 on top of there, that's 5 or 6 times the charge. That means the strength of the field and the force would be getting larger. So we'll remember that picture, okay? Let's clear the screen. I think it'll work. There we go. We can even erase this guy. There we go. Okay, and now what if we put some negatives in here? Let's put one there. And it said we can experiment and do them anywhere we want. What if we don't put them all on top of each other? What if we make like a bar out of them? And you notice that when you put them near each other, they and they're not all right next to each other, the arrows seem to do something weird. They always point inward, but then when there's like 2 negatives nearby, does everyone see the shape that's being created? There's something interesting here where they're starting to curve. And the electric field, right, tends to create these bends or curves in it. So we're going to go back and kind of finish that up. Now, here's the problem. How do you draw something that's brighter or darker in color? Well, I might have the ability to kind of make the pen a little bit darker. So let's make the lines a little bit thicker. And it shows that the field was stronger. Whoa, that line got a little bit out of control. Okay. Should have picked somewhere in between. And then for negative charges, let me go back to my small pen size, right? Now the arrows don't point away. They point inward toward the negatives. And we made an interesting shape here. So all we proved is that electric fields surround charges and they show the direction of force that a positive test charge would feel, right? Which way and how strong would the force be? So that's the purpose of an electric field. It's to map out and show visually how would the force be pushing on it. And as it turns out, weather people do this all the time with wind. They make maps of where the wind is going, and that helps people who are either sailing or maybe just out and about, and they're hiking or they're camping, and they want to know which way the weather is coming from, and that tells them how to prepare for their day. So it's kind of like a bunch of vectors that show you the direction of force. So on that note, we'll wrap things up, and we'll let you get on to your 5 questions.